Hi, my name is Dr. Stephen Martin. I'm presenting my talk on characterizing the critical parameters for docking unmanned underwater vehicles. So I work for the U.S. Navy. I work for the Space and Naval Warfare Center in San Diego. So yes, we are hiring too, as long as the hiring freeze is over. Sorry, I've heard everybody say that from industry and government. I figured I'd just knock it out there. So why am I here? Why is a PhD talking about docking of underwater vehicles? Well, things are a little bit different in the ocean. Docking is hard. Why? Because A, GPS does not work below the surface of the ocean. RF attenuates very quickly, on the order of inches. And what you primarily are reliant on is acoustics, and hopefully more and more readily is optics. So why is this important? Well, number one, we would like to be able to offload data at very high rates. So acoustics is limited to on the order of I know many people in this audience never heard of this, but there's these things called modems that were like 9600 baud, and you spend a long time just trying to look at Yahoo. Well, that's still present in the ocean, and they're time delayed over the order of seconds. And we'd like to be able to recharge our systems, while they're currently out in the field, because launch and recovery of underwater systems is very expensive, and we'd like to get away from that. And it also helps in the reliable and repeatable recovery of UUVs. So right now, I hire a ship, it goes out, I drive alongside it, I grapple it with a grappling hook, and then I hook it up to a crane and I pull it on board. It would be nice if I just put something in, the vehicle drives up, it plugs in, and I pull it on board my ship. Again, it comes into cost and time. So as part of this, and this is part of the DARPA program, which is the Technical Undersea Network Architecture, what we wanted to look at is, what are the critical parameters associated with this? Right now, typically docks are more to the seafloor, so you have the earth, which holds it in bay. We're not going to be having that anymore. We're going to have a free-floating dock. And why is this hard? Why have people been trying to do this for 20 years and largely been unsuccessful? And, one of the things I went back to my old, control days, because that's what I am. I'm an experimentalist. I do control theory, navigation, and it's a docking problem at its core. And docking problems are defined by basically your update rate, your field of view, and I think that was what was going to go into success. By the way, this is a picture of our very nice, very large test tank. We have a Bailey bridge with a acoustics section in the center where we put in transducers for doing acoustic calibration. And this is what I was using for the majority of our testing. So the docking picture in particular is that one of the things that, as you can tell from any sort of industry these days, is everything is trying to get smaller. And we are getting away from having things like the seafloor restrained seafloor dock or having a very large platform to recover. The docking vehicle platform we were working with is a Rena 600 with a hovering module. So it's a very, boutique system. It's one of two systems in the world that exist. This allowed for very precision alignment and docking. Part of the reason we did this is so that we could use it in the testing rather than the ocean. We used a acoustic, bentho-stack acoustic directional acoustic transponder, which is basically a USBL. Which provided both the initial acoustic positioning and messaging, and then and this is done at 0.4 hertz. Basically, anywhere from 1,000 to 10,000 meters. This is what handles the long range positioning problem, and we actually calibrated to this very unique system. Now, how are we doing this? What are we doing this different? And the thing we were trying to do is we integrated basically 4 photodiodes into a subsea housing. And what that enabled is it was used for the terminal, what we call terminal docking, which is basically the last 10 to 20 meters. And it had a very high update rate, 14 hertz, which is very large for the ocean. And the range of it is based on water clarity.
So, and basically what I did was a waypoint problem. I used it as a navigation sensor, which is what the equation is for. And what's different here is what you would normally see in control literature is that I don't have direct access to the vehicle itself. It's vehicle control. What I have access to is to send waypoints to it. So what I basically added was a payload computer, which computed a position I want the vehicle to go to, which I sent to the vehicle. And that is not the optimal way of doing it, but from our perspective, we would like the ability to have greater. The idea is that there are many underwater vehicles out there, and what would be nice is we have one common architecture that we use for doing docking, and we use these interfaces to send this data. So basically what I did was I took the world position of the vehicle, I transformed it to the body frame. I used the X and Y position computed by the object detector. I computed essentially a offset in both heading and elevation, and then a delta range I wanted to go to, and then I added it to my body frame position and transformed it back into the world frame. Easy, right? Now, what we were trying to do here is doing it in both what we call soft docking and hard docking. So one of the things that's actually becoming very prevalent in the underwater environment is that you can both do optical communication and hard docking. So optical communication is doing things like LEDs. Norm Farr presented this years ago. He's got an LED system which is called the BlueComs. And it's a great system. You get megabit level communication at whatever your water clarity enables. And what we're looking at is, can you go and have this thing hold station on the light and maintain a comms link? And this is the docking sequence we did, which basically the vehicle, it descended to depth, it discerned its acoustic position, it got into an optical alignment with the node, and then slowly worked its way in. So the closer it gets, the harder it is. And what we did was we were actually able to show that it worked. And we were able to show it worked with a very uncalibrated system to move the dock, which is basically a Navy diver. You grab a hold of the dock and you swim the dock back and forth, and as you can see from the figure on the right, the vehicle moved with the dock. That's what that's showing there. And we actually got to the point it was very reliable. We did it 10 times in a row for our different collaborators showed up, and I showed it one after the other. And the cool thing was the whole thing involved lots of duct tape and zip ties, which showed exactly how well I calibrated the system. The second phase was doing hard docking. Now, hard docking is actually what we classically feel is docking, which is basically you have an underwater vehicle, it docks into a cone-shaped node, and what that enables is very high data transfer rates. So you can either use optical techniques, which is you're very close, you can go much faster, and you can actually transfer power at the same time. It is a very similar docking sequence, and there's a figure of the vehicle actually being docked into a node there. We did it repeatedly. I did a number of tests with this. We got, at the end, I did, 31 docks right in a row with one miss. And anyway, videos. They're very cute. So this is a video of our test sequence in November. Basically, you have the vehicle descending to depth here. You can see our little camera ran in the background. Gets in position. The vehicle propelling forward is basically, what you have here is a 12-foot vehicle. I have hovering modules on it, but it's not the most stable system when it's going from the surface down. So it kind of stabilizes, which is what you're seeing here. It'll back up, hold station, it'll transmit a number of acoustic packets. Functionally, in an operational system, you hopefully not use these hovering modules, you're just using propeller. You can do this at longer distances at that point. So you can see the vehicle's backing up to its proper position. Part of the reason for that is the acoustics in our facility were not great, so you kind of had a good sweet spot to work from. And then at this point, you're going to see it come in a dock. And as a guy that originally was one of the original fathers of this technology, think of it as a Stinger missile, right? You have, you're following, in this case it's a light, and you're following it into the dock, and you can see the light is in the center of the dock. And it's now at this point, it's just kind of rattling it to the dock. I got another video too. And the reason for the flashing of the LEDs is basically to distinguish it from sunlight. So it's actually flashing at 40 hertz. So that's different from sunlight, which is just a constant thing. And here it is doing it again. So the key thing is, one of the things we're trying to show here in terms of videos and repeatability of the system is, one time you're lucky, 2 times in a row, okay, well, maybe you're not getting lucky. If you do it 30 times in a row, okay, maybe you have something there. But the key thing we found from this is, when I came into this is that, at first I thought it was going to be easy. Because, of course, we all know what we're doing. We're all roboticists. Everything is easy. But in this case, the hard part is these vehicles had very expensive sensors on them. It had a $150,000 profile INS, a $30,000 DVL, $10,000 paracentric depth sensor. But those sensors, depth is an absolute measurement because it's pressure. But the INS and the DVL are relative measurements. So you relatively know where you are very well, but you don't absolutely know where you are. So you absolutely have to know where you are absolutely well. And that is where the light comes in. Because in terms of acoustics, the problem is, if you can see there, you have this little thing hanging down. That's our acoustic transducer. Well, that thing is, at the very least, you're not going to see it for the last 3 meters. And then you're going to go, you're going to lose that, you're going to have 3 meters where you're going blind, which is basically the most important part of the whole process, which is when you dock. And the other thing is, you're going to have shadowing because it's an acoustic transducer, it's not right in front. And again, you're going to go blind, which is right when you need it. So, the other thing we looked at in this process is update rates. So, what we found was that actually not only because what I did was I subsampled the optical data, and you found that as you slow down the update rate, speed meant that you were going to miss the dock more and more. So again, it's a control problem. So in closing, docking requires sensor update rates greater than 2 hertz, preferably at least 10 hertz. We felt that in order to do this, and I mentioned this briefly, and we go into it later in our acid testing, is that the minimal in-water mass ratio between the subsea docking and ADV is 5:1. So basically, because you would think it's a non-holonomic system, but actually what it is it's an unconstrained system that is holonomic. So when you push against it, it doesn't push back. So it's like if you were to put a toy in your pool and you push it with a broom. It's just going to move away. It's not going to push against you. So you have to have something with enough mass to push against you to actually restrain the vehicle so it can dock. And the third point, which came into importance for other applications, is that it is possible to have AVs dock using this basically this backseat driver or sitting at waypoints. And where that became important is that you have delays in the system, which is basically worked out to being, a sample to measure, a sample to transmit, and a sample to understand it and transfer back. So 3 samples, 1/3, 1/3 of a second. I would like to thank our sponsor, the Defense DARPA, their SDO office, our team at SSC, and then the dive locker, which again, they truly were able to help us out, and they were saying it was really cool.